Okay, well, welcome to the webinar. My name is John Linford. I'm an applications engineer at Arm, and today I'll be talking about tips and tricks for porting HPC applications to Arm-based systems. Now, Arm is really changing the game in HPC right now. We just had Sandia's Astra supercomputer become the first Arm-based system in the top 500 list. This is a huge proof point for us. It really shows that Arm has arrived in HPC, and we're enormously excited about the potential we have here. Um, NNSA is experiencing some unprecedented speedups for the mission-critical applications, and you may have seen the news coming out of Sandia, coming out of Bristol, coming out of Riken, that ARM-based HPC systems have this amazing ability to accelerate applications. And you're probably wondering, what's the catch, right? There's no free lunch. So what's special about ARM-based CPUs, and do I need to change anything in my applications to port them to an ARM-based system? Will this work for me, and what do I have to do to make it work? So that's what I'm hoping to address today. I'm going to spend about 25 minutes talking about who ARM are and what we can do for you. I'll show you how we can port HPC applications to ARM-based systems and go over some of the basics for that porting process. And then we'll end with a question and answer session so you can drill into the topics that you care about. So our partners usually engage with ARM on CPUs in one of two ways. ARM provides a core license, which is just we hand the partner, a mostly built SoC. So it's a complete microarchitecture to design with flexible configuration options, and then the partner can add their own IP and their own distinguishers to turn that into a valuable product. A more powerful long-term strategic investment is an architecture license where the partner designs their own complete CPU microarchitecture from scratch and has no reference to ARM core designs. This gives them the complete freedom to develop just about any design as long as it conforms to the rules of the ARM architecture. So their end product has to pass a validation so that we know that the software is still compatible, right? We have to be able to assert that anything compiled for ARM v8 or ARM v9 will run on an ARM v8 or ARM v9 chip, regardless of who actually built it. Now, I kind of like to think of this in a silly way as a take and bake pizza. Okay, so ARM is like the take and bake pizza of the CPU world. The core license would be if you were just to take a frozen pizza, and then if you felt like it, you could add your own toppings, you could bake it for different times, but what comes out at the end is still more or less what you started with. It just has a few distinguishing features. The architecture license would be like if the pizza the pizza factory were to sell you the recipe for the pizza. So you have a lot more freedom in how that pizza is assembled and what goes into it. But at the end of the day, it's still a pizza, right? You're following a pizza recipe, so you're not going to accidentally somehow get a chicken dinner. In the same way, if you get an architecture license from ARM, you are going to get an ARM-based CPU. It'll never be an x86 CPU, but it'll be an ARM CPU. But you have a lot of freedom on how that CPU operates and what its strengths will be. This whole model of engaging with partners and developing different products at all layers of the stack and allowing our partners a lot of freedom to go and distinguish themselves with their own IP has led to this complete ecosystem that we see today. So for example, this is a demonstration I did back in June where I ran the OpenFOAM CFD application on a cluster of about 100 Cavium ThunderX2 cores. Cavium ThunderX2 is the flagship CPU, I would say, at the moment in the ARM HPC space. It's the one that Astra's developed on, it's the one Isambard has developed on, and for the time being, the ThunderX2 really is the core for HPC or core for ARM in HPC. So I was able to run OpenFOAM on the ThunderX2 cluster and then render ParaView in a headless configuration so that the frames were being sent over the network over VNC. And then I used ARM's Neon vector extensions to accelerate that process. On the other end of the network, I connected a Windows 10 laptop that was running the Qualcomm Snapdragon SoC. So the CPU and the GPU are actually from ARM. So in the end, we could see real-time CFD streamlines and everything flowing over this motorcycle model. and it looked really cool. And the whole thing was completely ARM, right? It was ARM CPUs and GPUs end to end. And that's only part possible because of ARM's unique business model. It's the only possible through this process of enablement, co-design, and partnership. Now, before I get into the tips and tricks, I want to talk about ARM's software offerings. So I've shown you how how ARM licenses IP to build CPUs, but how about on the software stack? Well, ARM's solution for HPC applications is called the ARM Millennia Studio, and this combines cross-platform tools that run on ARM, x86, Power, and GPUs like NVIDIA GPUs, and with ARM-specific tools like the ARM compilers and the ARM performance libraries. So together, those things are called the ARM Millennia Studio, and I'll be referencing this pretty much throughout the talk. The ARM compiler is built on top of LLVM and uses the Clang and the Flame projects for the compiler front end. So it's built on a completely open source framework, and ARM actually upstreams a lot of its developments back to LLVM. It's not like we deliberately hold anything back for a year, or there's no policy of doing that. ARM is very open in enabling LLVM to run well on ARM, and this has had a lot of good benefits for ARM and for the community in general. Alongside the compilers, there's the ARM performance libraries. These are really powerful, highly optimized math libraries for BLAS, LAPACK, and FFT. And they also ship with some optimized math intrinsic libraries. So POW, exponent, log, sine, cosine, tan. These types of functions, we've developed a highly optimized version of the math library that ships alongside the performance libraries. And I'll talk about that more in just a bit. ARM Forge is the cross-platform component of the ARM Millennia Studio. It's a combination of a debugger and a profiler, both that came from the Alenia company that ARM purchased a few years ago. So Forge is available on the vast majority of the top 500 machines out there right now, and it fully supports ARM, x86, IBM Power, and NVIDIA GPUs. And it's a really good way to create a performance bridge between the existing systems and the future systems, which we hope will be ARM-based. So you can take a profile of your current application on the current system and then compare it to the profile on an ARM-based system to see how your application performs when more memory bandwidth is available or when wider vector units are available or what have you. ARM Performance Reports is another cross-platform tool. It's kind of like a consultant in a box. It can show you in plain English where your application is slow or where there might be bottlenecks in the code and give you some advice about how you might be able to accelerate that application or how you might be able to address those bottlenecks. So this ARM Millennia Studio, I'm going to assume for the remainder of my talk that this is how you are porting your application. There is a whole suite of open source application or open source tools out there. The GNU compilers work great on ARM. There are many open source profilers and debuggers, but I'm going to focus on ARM's software stack in particular, mainly out of concern for time. If you want me to talk about the open source stuff, I'd be very glad to. Just please bring it up in the Q&A. So the first thing you want to do when you start porting your application is think about your application's dependencies. Now, most HPC applications, most scientific software is quite monolithic, but it's usually not self-contained. It's going to depend on I/O libraries like HDF5 or NetCDF or linear solvers like Trilinos. It's almost always built against some layer, some communications layer. So OpenMPI, OpenUCX, Charm++, something like this to enable parallelism. There are also applications that build on Cocos or Raja where these portability frameworks try to abstract even further from the hardware. Now, the good news for you is that the enormous majority of these dependencies have already been ported to ARM. And if you go to the ARM packages wiki, then you can see recipes on exactly how to build these libraries and dependencies. So the ARM packages wiki is here. This is the URL, and I strongly recommend before you start your porting effort, go check, go make sure maybe somebody's actually ported the application you're interested in. It may already, in fact, be on ARM. If it's not, then the dependencies likely are. Anyone can join and contribute to this, and we highly encourage you to if you have an application, even a closed source application, but you can provide a recipe for building it and running it on ARM. Feel free to create an account, dive in, and create a wiki page for it. So once you know your dependencies are all available and you're going to build something, make sure you're using the right compiler. I see this a lot, in fact, that make files or build systems, make assumptions about compilers, or if you don't you explicitly specify certain compilers, it'll just default to GCC and never tell you. So if you want to use the ARM compiler for HPC, be very specific on selecting it. The C compiler is called ARMclang, the C++ compiler is called ARMclang++, and the Fortran compiler is called ARMflang. You can specify them as I've shown here, or you might have to use the custom flags on your configure command line, or if you have a really odd build system, which unfortunately there's a lot of those around, you might have to edit files to specify the compilers. Typically, this is not too difficult. What is difficult and can be very dangerous is if the build system silently selects a compiler in the case of failure. So maybe you have GCC or ICC hard-coded into a file somewhere, and then when you build, some condition causes that hard-coded compiler to be invoked rather than the ARM compiler that you selected, and suddenly your performance is just terrible because you picked up a GCC 4.8 that the system provides, right? You have to watch out for this. If you're using a well-designed, well-supported build system, this won't be a problem. But unfortunately, many HPC applications and legacy applications have homegrown customized build systems. So check your compile logs and look for invocations of GCC, or if performance is really, really poor, just make sure that you're actually using the compiler you think you're using. Related to this is be sure you're using the right compiler flags. So in general, always start with the -o fast -mcpu equals native flags. These work for both C's and the C++ compiler and the Fortran compiler. OFast should give you maximum optimization. It should really go as fast as possible. The mcpu equals native is critical. This enables the compiler to use things like LSE atomics on the Thunder X2 and take advantage of architecture-specific or micro-architecture-specific features in the CPU. If you don't specify this, the compiler should make the right decision, but it's really a good idea to just add it there and make sure that you're getting a binary that's optimized for the CPU that you intend. Now, if Fortran runs into some issues, you might want to try the F no stack arrays option to force automatic arrays onto the heap. By default, OFast will put arrays on the stack for performance. And if your stack size is limited and your Fortran arrays are very large, you're going to segfault at runtime. So add -F no stack arrays if you start to run into these issues. OFast will also enable certain optimizations for floating point arithmetic. So if you are getting wrong results due to reordering of math operations, use -O3 -FPP contract equals fast. This will give you some better performance. It's a nice mid ground between OFast and O3. But if this still does not produce correct results, then drop it down to -O3. O3 should give you general optimization without violating the floating point contracts and give you very good performance on floating point. This is always a question for some reason. Yes, ARM is IEEE compliant floating point. There's no weirdness here. You don't have to make any special considerations. This is not cell broadband engine. We've cut no corners. You can go ahead and run floating point exactly as you expect. The next thing you want to do is make sure you're using the right MPI compiler. I get this question a lot. People ask, what is the best MPI for ARM? And really, it's a trick question because ARM is no different from other architectures in this regard. There is no quote best MPI. That depends on your needs. It depends on your application. Depends on a lot of factors. So the crucial thing is that OpenMPI, MVOPitch, and MPitch are all very well tested on ARM. You can go to the the package wiki for build recipes, but typically these things work well out of the box, with the exception currently of MPitch. Uh, the next thing you want to do is once you have OpenMPI configured and built with your right compiler, make sure that the MPI compiler wrapper you're using actually invokes the compiler you expect. Use the mpi-cc-show command to list the compiler that's getting invoked and the compiler options when you do mpi-cc. This also works for MPI fork, of course. So you want to double check your C compiler, your C++ compiler, and your Fortran compiler. Don't just assume that they're invoking the ARM compiler because that's your serial compiler. The MPI compiler wrapper might be doing something different under the hood. So definitely double check that. I mentioned ARM performance libraries earlier, and now it really is key for getting good performance, especially on systems like ThunderX2, that you link against the ARM performance libraries. Starting with the HPC compiler 19.0, you can use the -armpl flag to link your application against ARMPL. This is a really nice and easy way to get a solid performance boost. For example, you can see here's dgem performance on 56 threads of Cavium ThunderX2, comparing Bliss, OpenBLAS, and ARMPL 19.0. And you can see we're getting a solid 100 gigaflops or so additional for certain matrix sizes. So it really is important to link against this if you're calling BLAS, LAPACK, or FFTs. FFTs in particular can be up to 3 times faster with the ARM performance library. In this chart, if you're below the blue line at 1, that means FFTW is faster. If you're above the blue line, then ARM performance libraries are faster. So as you can see, for many, many sizes of FFT, ARMPL outperforms FFTW by a good margin. Again, just link with -armpl with the ARM performance or ARM HPC compiler to get ARM performance libraries. Dash LA math is a really useful flag as well. So this will link in an optimized version of the math library. This is actually an open source project that ARM has put out on GitHub. So ARM has the ARM optimized math routines. A compiled version of this ships with the ARM commercial compiler, but you can download this and use it with the GNU compilers as well. This math library includes single and double precision implementations of exponent, power, and log, and also implementations of sine and cosine, and it's expanding all the time. You can see significant performance benefits from linking against this library if your application calls a lot of transcendental functions. So for example, in this chart, if I look at the performance of Wharf with GCC and use that as my baseline, then you can see I get a slight performance bump when I compile Wharf with the ARM compiler, but then performance is enormously improved by linking against this ARM optimized routines libamath library. If you look at Cloverleaf, you'll see, interestingly, there's no performance gain from using ARM optimized math routines because Cloverleaf is not compute intense, right? It's not invoking ARM, it's not invoking exponent and power and log. It's more of a memory movement benchmark. So naturally, the performance is unchanged by linking again in the math library. But codes like Wharf and Branson show a significant performance gain from linking against this, and there's a good chance yours will too if it's compute bound. As you're porting your code, you might want to take a look at vectorization and improving the performance of your code through vectorization. One good way to do this is use the compiler optimization remarks. Compiler optimization remarks will tell you what has been vectorized and what you might be able to do to improve vectorization. You pass in certain regular expressions. Now, what I've shown in the slide is actually verbatim what you would put on the command line. So rpass equals backslash parenthesis loop vectorize backslash pipe inline backslash parenthesis backslash, right? This is what goes on the command line. And what comes out of the compiler looks a bit like this. You'll get remarks showing what loops are vectorized at what width and what interleave count. This works both for the C compiler, arm-clang, and the Fortran compiler, arm-flang. You can also improve vectorization by using compiler directives. Many of the OpenMP directives are supported by the ARM compiler, so you can use pragma IV-dep or the directive IV-dep in Fortran. This will ignore potential memory dependencies and vectorize the loop. You can also use OMP SIMD in both C and Fortran to indicate that a loop can be transformed into a SIMD loop. If you really want to force vectorization, you can say vector always. This forces the compiler to vectorize a loop irrespective of any potential performance implications. In my experience, IV-dep is usually a better way to go. It's usually better to hint to the compiler that vectorization is possible rather than force the compiler to vectorize when it advises that you should not. It's often the case that the compiler knows what it's doing when it refuses to vectorize a loop, and forcing vectorization may in fact harm performance. Conversely, you can disable vectorization. This might be useful if you're trying to benchmark serial codes versus vector codes to really quantify what is the benefit of using vectorization in this code. There's also a number of Clang compiler directives for C and C++ that you can use. For example, you can control the unroll count for a scalar loop, or you can control the interleave count to force loops to interleave by a certain factor. It's really important that you stick to the standard for your language. Don't rely on non-standard extensions. Just don't. Unfortunately, a lot of old Fortran codes will use very, very, very long lines or compiler-specific intrinsics or something that just is non-standard. If you deviate from the standard, then my best advice to you is to clean up your code. Actually do follow the standard. Now, ARM compiler has been as forgiving as they possibly can, and in many cases where we have key customer codes where they just cannot, for whatever reason, change the source, we've been able to work with them and expand the compiler a little bit and fudge it a little bit to accommodate their broken code. But in general, this is not a good way to do things. So we do strongly recommend that you follow the standard. And if your compiler is complaining because you didn't return an integer from an integer function or something like that, just go return an integer. It's not that hard. Related to this, the Fortran compiler is always expanding. The C++ compiler is always developing. There's a lot of work to be done constantly. So if you're wondering, is language feature X supported by the Arm HPC compiler? Well, you can go check these websites, and it'll show you exactly what features are supported, and give you an idea if it's a problem of your code deviating from the standard, or if our compiler just hasn't reached that point of implementing the standard yet. One little thing. This actually cost me a day of my life once. You do need a license to run the Arm HPC compiler, and that license is going to get checked out every time the compiler is invoked. And this can lead to some surprising results if you're changing environments between users. So commonly, you'll see something like sudo make install at the end of an installation, right? If you want to install something as root. The challenge is if the root environment doesn't have the compiler license configured, you'll see some really odd error messages coming out of libtool. For example, you might see libtool claiming that the arm-clang compiler cannot be found, and this will make just no sense. Easiest way to do this, break the installation into a few steps. Do a sudo-i to get an interactive shell as root. Configure the compiler license environment variables or whatever you need to do so that the compiler license can be found, and then make install. It's actually very easy to work around, but the error messages can be quite surprising and non-intuitive if you don't realize that you're changing environments and therefore losing the environment variable that guides the compiler to the license. Another problem with libtool, but this one is becoming less and less frequent, is that if you have a really old, outdated libtool, it might not be able to identify the ARM compiler, and it might not be able to pass the right flags for the position independent code into libtool. So what you can do is after you run the configure command, run these two sed commands to modify the libtool script. And the good news is if there's no issue in your libtool, then these sed commands are harmless. If your libtool is out of date and isn't working on ARM, then this will fix the problem. So it's a real easy fix. Another one that I have not seen in the real world in a long while, and problem is mainly solved at this point, is that some older config.guess files aren't able to identify the platform. Good news is if you execute these wget commands, it'll download updated versions of config.guess and config.sub, and problem goes away. Again, I haven't seen this one in about a year, but if you're running with a really old code, there's a good chance it might crop up. One thing I do see fairly regularly is that test suites don't work, right? So if your test suite is written to expect binary identical results across platforms, you're going to have to update your test suite. So changes in compiler and changes in platform mean that there will be, you know, usually insignificant differences in binary output. And you do need to make sure that if your test asserts that two binary outputs are completely identical, you might need to develop a richer metric for comparing binaries, or you might need to have a different baseline set for ARM that you use when you're running on ARM. It doesn't mean it's wrong, or a better way to say this is probably that all platforms are equally wrong when it comes to floating point. If you can't, you're going to get equally wrong answers as you change platforms. So just because you wrote a test suite doesn't mean it stays fixed. You have to constantly keep your test suite up to date and think about how do I need to expand this for ARM and keep it up to date as I port my application to a new architecture. Something really unique and specific to ARM, especially compared to other main architectures out there, is that ARM uses a weak memory model that allows reads and writes to be reordered. Okay, this usually manifests in strange sort of like race condition type failures where in multi-threaded codes, and it's almost always related to some lock-free thread interaction implementation. Now, first, this is a very rare symptom in application code, and in fact, languages that specify a memory model like C++ make this impossible because the language memory model is going to supersede whatever the hardware provides. If you're an application developer, you can effectively forget about it. If all you care about is just your science, then ARM's weak memory model doesn't mean anything for you. You can just tune out until I change to the next slide. However, if you are seeing weird errors in shared memory code or MPI, certain MPI implementations have race conditions while other ones don't, this could be because of the weak memory model, and that you might have to report the bug back to the MPI implementer. If you're developing a user level threading library, then you should be aware of this. You might have to think about adding some explicit barriers between loads and stores to make sure things are happening in the order that you need. But again, generally for application developers, this is not a problem you'll see in the real world. One thing you might see, this is more relevant to the application developers than to the library developers, is that ARM treats integer division by zero differently from x86. This is specific to integer division. It is not floating point division. This is only for integers. On ARM, if you take an integer and divide it by zero, the answer will be 0. On x86, if you take an integer and you divide it by 0, the answer is a floating point exception. Now, there's no standard that specifies the right way to do this. There are, design reasons why x86 went one way and ARM went another way. For you, the application developer, this means two things. First, check your test suite. Make sure that you're not relying in some way on a division by zero, that you're not expecting it to raise a floating point exception. And also, when you're debugging a code, don't try to trigger, division by zero as a way to stop the code or to use this to raise a signal. Division by zero is zero on ARM. There are ways to catch this in software, and we can talk about that in Q&A if you're interested. But typically, it's best to avoid dividing by zero, at least I find. So in summary, I provided some references, additional resources for the end of this. This is just a quick summary of the ARM porting cheat sheet. It goes through all the slides I've shown here. It's a good way to just step through and make sure your application is ported correctly. For additional resources, we'll take a few minutes here to recap. We have the ARM HPC ecosystem website. This is arm.com/HPC. This will give you all the latest news, blogs, quick start guides, links to community collaboration sites. This really should be your go-to place for keeping in touch with the ARM community. The HPC community also has blogs, calendar, and a forum over on community.arm.com. This is really a community-driven content, so go there. You can ask questions, share progress, and just interact with other people working in HPC on ARM. And finally, here's some links to useful websites that I recommend you go and try. So thank you very much for your time, and I'd like to know if there are any questions. Thank you very much.